So we're continuing on our investigation of getting this 8x8 RGB LED matrix up and running. One thing I found out pretty quickly is that using individual jumpers and hooking them up to individual pins was going to be a real pain in the neck. So I went and got some ribbon cable and hooked, 32 pieces of this ribbon cable onto a breadboard. And I pulled out the old Arduino and see if we can get this Arduino controlling the LEDs. Now, obviously, having 32 pins, which is 8 for the 8 rows and 8 each for the RGB channels, you don't have 32 output pins on the Arduino. So we need to go into what's called a shift register. The shift register is that pin you see, is that chip you see right there. What a shift register does is allows you to use one data output here and a couple of control wires to actually serially shift out up to 8 bits in a single chip, and then it will use its own output pins to display those bits. A little complex to try to explain, but basically using one output pin to control 8 output pins on the chip. So you actually gain 8 pins. You do need a couple of control pins. So you're really getting 8 for 3. Furthermore, you can chain these shift registers, so you get 16, 32, however many you want as you keep chaining these things on, all for just 3 pins on the Arduino. So to program that up, actually this is a neat little tool. I have it on my Nexus 7. It's an Android tool called ElectroDroid, and it has all these neat kind of things. It's $2 or $3, but it's found it's well worth it. If you go to resources and ChipDB, you can then search for the this is a 595 shift register, and it's this one here. And so you can actually see the pinouts for that. So pin 15 is output channel 0, and 1 through 7 are the other 8 output channels. 16 is the positive voltage, 8 is ground. 13 is your enable pin, that has to be pulled low, and 10 is your reset pin, that should be pulled high. And then Q7 pin 9, that you would use that to chain other shift registers. So the 3 important ones here are pin 14, which is DS labeled here. That's your data pin. That's where you send bits in. 11 is your serial clock, or sometimes just called clock pin. This is where you tell it when you're sending each bit in. And 12 is your, they call it the register clock, or sometimes the latch pin. This is where you say, okay, I'm done sending everything. Use the data I sent in to set my outputs. So this is what we have here. We have the yellow, that's the voltage in. Blue one over here is the ground. Pin 15 and all the rest of the ones on the left-hand side are the outputs. And I have, this is the enable. This has to be, actually not enable. This is the enable pin. This has to be set to ground. Otherwise, it won't be enabled. And if it's left floating, you can get some really weird things happening that just aren't right. And this is your reset pin. This should be held high, or if it's floating again, it might go low and reset all your registers. And then these are the other 3 pins here, your data and your clock and your latch, and those go to the Arduino. Of course, the Arduino, we're also sending out, oops, that came loose here. We're also sending out 5 volts and ground to our breadboard. So what happens is we're using, and I'll show this in the software, we're using these 3 wires to send input into the chip, and then the output goes up here into this other chip. And what that is, it's a dip resistor. It's basically 7 330 ohm resistors in a dual inline package. Just saves me from having to plug in 8 different resistors. Because I do need 8, so this is only 7 in there, so I have an extra one there. And those go through the resistors into this ribbon cable into pins 1 to 8, which is the blue channel. And I've hooked up pin 17 here to positive voltage. So we're controlling the first row blue channel. So depending on what we send into the shift register, we're going to get something on the matrix. Let's take a quick look at the software here. I've set my data, latch, and clock pins as variables there. I've set them up as output channels. And so what you do is you sandwich all your writing in between sending the latch pin low and latch pin high. So we set it low, we do all our writing, and we set it high. And up here I have the data that I want to set. I have 1, 0, 1, 1, 0, 1, 1, 1. So it's 1, 1, 2 1s, and 3 1s. And I'm looping through that backwards because basically as I shift those in, I want to shift the last one in first so that it's at the end. And then the last one that I shift in will be at the beginning, and these will come in the correct order on the output pins. So I'm looping through this array backwards from 7 to 0. And for each bit, I'm setting the clock pin low, setting the data, and then setting the clock pin high. And when I'm all done with that, then I set the latch high, and that sends all those bits to the output pins and then into the matrix itself. Now, again, so we have 1, 0, 1, 1, 0, 1, 1, 1. Now, if we look over here, what we have is we actually have, you might expect that we have on, off, on, off, on. We actually have the exact reverse of that, which seems like a bug at first, but if you think about it, this is a common anode, which means the positive voltage comes in here to all the LEDs in that row, goes through the LEDs and back through all this stuff into the output channels. Now, if those are high, then you're going to have positive on both sides of the LED, and it's not going to light up. If those are low, then the current can go through the anode, through the LED, into the output pins to ground, and you will have light. So actually, what we have here is that where the output is 0, we get a light, and where the output is 1, we get no light. So we could change this all to, reverse the 1s and 0s, but that's kind of goes against what you usually think of binary. 1 is on and 0 is off. So you can make a really easy trick to fix that is before we send the data here, we just use the not operator, which means if it's 1 or true, it's going to set it to 0. If it's 0, it's going to set it to 1. And so if we run that, now we have the correct thing. We have 1, 0, 1, 1, 0, 1, 1, 1. And so that's basically it. We've lit up the first row. And we could put any pattern in here just by changing the numbers we set in this array. Now there's another way to do this, which I'm going to show you here. Actually, I'm going to show you. Oops. Oh yeah, there we go. It's not what I wanted to show you at all. Let's try this again. I love Windows. Do this with the keyboard. Yeah, there we go. All right, so here's another sketch I did. Basically, the data and the setup is the same. I don't have the array here. What I'm doing is I'm calling this shift out function, and I can pass that a binary number. So I'm using the same number 1011 10111. And I pass to this shift out function, which takes my data pin and my clock pin. And actually, I'm going to change something here. I'm going to change that LSB first. That's least significant bit first, which is going to put the lowest bit in first and the highest bit in last. And again, if I run this, we get the same thing. Pretty sure that ran. Yeah, so we get the same thing. We can verify that by changing this number. So make that a 1. Run it again. And okay, so that did change. So we are doing that correctly. Again, if we change this, and also notice that here I'm using the binary not, again, because the ones will become no light and the zeros will become light. So this is the binary not operator. It just shifts all the bits to their complementary number. Let me just change this back. And if we change this to MSB first and run that again, we should get the opposite. Come on. Oh, something wrong here. A typo. There we go. Now we have the most significant bit and then going backwards. And there's one other thing I did with this. And do a little animation here. Basically the same setup again. And this time I'm going, I put a for loop in there. And I'm shifting out this number. This I left shift 0 through 8 times. You know, I's 1 left shift I, which is going to loop through this array 0 to 8 times. And this is going to give you these numbers here. So this is what I'm shifting out. So we should have an animation because I'm going to wait 1/10 of a second here between each of these. So the LED should shift from right to left as it goes through. Let's see what happens. Yeah, great. So it does that. So yeah, that's what we got. We got the Arduino controlling a single row with animation in one color. So my next plan is to throw another shift register in there and get 2 colors, hopefully chaining them, and then eventually a third one for 3 colors, and then a 4th shift register to control the rows, and then I should be able to control every single LED on this, any color, through 3 output pins. We'll see how that goes. Goodbye.